So hi, my name's Andy Clark. I run a team of developers working for Mountain Warehouse. We do all the kind of back-end stuff. So on a day-to-day, pretty much we don't have users, we have data flows. We're squirting data from our company out to third parties and vice versa, getting sales in, getting orders out, getting stock in, getting movements out, that kind of thing. And every year we do a hackathon. And I was tasked with the job of coming up with a prize for the hackathon. And I picked this little yellow board because it was A, it was the right price, and B, I thought I can get dotNet running on it. So, that's real. Just gonna switch to slides. Oh. Right. So, why did I think this was a good idea? So as I mentioned, we've got kind of a lot of back-end systems. There's no interaction, there's no user interface. And I thought it would be good if people could have something they could literally physically hold in their hands, press buttons on, tap on the screen, see results instantaneously and have a much more kind of immersive, interactive experience with their prize. So for the prize, I just put some simple graphics on it, which that was roughly that demo was based on. So today I'm going to go through all the different kind of steps of how I did that, what kind of problems I had, and how you could do it yourselves. Okay, so what is nanoFramework? So you get quite a lot for your book. Basically, nanoFramework replaces all the kind of things that you're used to having on your computer. So things like operating systems, device drivers, that kind of thing. Right at the bottom level, it's talking to the hardware. And obviously lots of different devices. I've got lots of different types of hardware. We're going to look at a couple of common ones, displays and touch screens today. And then coming up from that, we've got the hardware abstraction level. So that allows the higher levels to talk to the hardware without having to know the very specifics of it. The platform abstraction layer, which is kind of almost like the operating system replacement. It does things like memory management, networks, things like clocks and times, etc. So all stuff you take for granted on a desktop computer or a server, having a clock is actually an optional extra on these small devices. And then stuff that you might recognize, CLR, all the kind of usual execution engine, type management, even garbage collection, etc. And some basic functions. And then the PCL.
Base class library?
Base class library, well done. Is basically a series of standard libraries that you can add on top of all the other stuff. And then finally, the code that you get to write is the fun bit. Okay. So, getting started. Most of these devices don't come with nanoFramework on it, so you need to get what they call the firmware or an image onto that device. And you use a tool called nanoF, which I foolishly thought was a little piece of software until I tried to download it on the train today and it was 140 megabytes. But that basically talks to all these various devices and sticks the images onto those machines. It can also do the interrogation and tell you what the capabilities of the machine are. Okay. Also need to talk about libraries. So again, we're used to like NuGet and just being able to pull libraries in left, right, and center. If we think back to that image for a second, what we've got is some of the stuff is here in the CLR level, and then some of the stuff's in the system library level. So if we want to talk through here, it's almost like you have to get the right version. So it's like if your machine doesn't have dotNet 5 on it and you've deployed for dotNet 5, then it won't compile. And it's the same here with these kind of libraries. And we'll see when we dig into that in a second how that all works. Yeah, in fact, let's do that. So, Visual Studio. Nope. Don't have to press stop on this then. End. Right. So here we are in Visual Studio. You might recognize the kind of standard stuff. Here's our various libraries. So I've got one for ESP32, which is the chip behind this device. There's a standard events library and a GPIO library. For those that don't work with a lot of embedded systems or play with a Raspberry Pi, GPIO stands for General Purpose Input Output. So it's the basic level that allows us to turn output pins on and off. And a lot of these devices come with pins connected to various things. And this one I've got LEDs on, so I'm just going to flip it over. It's easy enough to do it that way. Bink. So here's the processor itself, little aerial on it. This thing here is a 3-color LED, so we're going to flash one of those in a little minute. What do we got down here? The bottom, there's a display chip. We've got an audio chip. Big silver box is a compact flash, SD card. Across on the right is the USB that does the debugging and all the image stuff. Then we've got a bit of power stuff on the right there. But most of the time you don't need to know all this because obviously the dotNet framework has kind of abstracted a lot of it away. So, back to Blinky. Okay. So, yeah. Other windows. Yeah, there we go. So one of the things that you need to make all this work is basically it's a plugin for Visual Studio. Classic extension as if you were working with any other kind of tools, like you might have an XML extension or you might have a extension for doing spell checking, etc. So there's a nanoFramework extension, and it provides various things like all of the default projects and some of the extra tools. One of them is this one. Let me just look to see if I've got anything connected. Hopefully I have. Here it is. So I've got an ESP32 generic display Rev 0. So that's the name of the image that's currently installed on this device, and it appears as a COM port. So pretty much all the various devices will have COM ports on them. And then we can use the tool nanoF to send. Oh, it's not very nice. Let's see. There we go. We can see that down the bottom there. We've got nanoF, platform ESP32, target ESP32, generic generic display Rev 0, serial port is COM5, and we're updating it, and that will put a new image on it. And everything runs basically on that little command line to get that first basic image on. And it also gets on the basic libraries. Now if we ask it what's on it, which is the device capabilities button, hopefully it will have a chat with the box and go, what have you got installed? Nope. Yep. Get the right window. Sorry, you see the proper mouse. So here we go. We've got a HAL build, nano CLR running ESP32, built with the set tools it was built with. As the target is this image that I've been using all along. Platform is ESP32, date, type, etc. And then if we scroll down, what we'll see is all of the assemblies that are installed on it. So screen test is the software that I've put on it. Then all these other bits and pieces are that BCL and PAL and HAL. And we see down here we've got all these various native assemblies as well. So if I go to NuGet, where is it hiding? It's probably easier if I bring it up from here. Resize that. That's a rather alarming message. Don't want to do that. Claims to be missing stuff. Well, there you go. I'm not on the internet at the moment, which is probably why it's not happy. Now, what do you know? You can't use NuGet while you're not on the web. Even to see what you've currently got installed. Okay, you're just going to take my word for it. So basically, if we'd search for these packages on the right hand side, we basically get two version numbers. There's the kind of the build version number, and then there's the version number of the image that it relates to. So if we just swizz back to those slides for a second. So basically, if I've got a UI element in my project, then my user NuGet package has to match the version of the version that's installed on the device. And if you don't do that, you'll get a load of errors and it complains. Pretty much what you have to do is go and upgrade or downgrade your NuGet packages so it matches the firmware on your board. Alternatively, you can upgrade your firmware on the board so it matches your software on your computer. Okay. Okay. Right. Let's get rid of NuGet then if it's not happy. So let's have a look at a bit of software. This is a very simple Hello World bit of software. So using statements, hopefully you recognize these. So we've got our system device GPIO, so we want to do stuff with input output. And then we've got a hardware abstraction layer for ESP32, which gives us some extra capabilities, which we'll look down in a second. So to talk to the input output, we create a GPI controller. And then on this board, we've got a 3-color LED, red, green and blue. So each of those is on a different I/O pin. So what's that say, 4, 16 and 17 for RG and B. And then we have to set those. In this case, we have to set them high because of the way the LEDs are driven is you have to take them low to turn them on and turn them high to turn them off. So we start off by setting them all to high, write a little debug message. So for those of you who worked with microcontrollers, putting debug messages into the code is actually a little bit unusual. You can't normally step through code on a microcontroller, but same as you would with like a console app or anything else, you can put breakpoints in, you can step through the code and generally see what's going on. You've got to be quite aware of what you're doing here though, because if you've got something that's timing sensitive and you're stepping through it, obviously that's going to mess up the timing completely. So you need to be a bit aware of where you put your debug statements and where you put your breakpoints, etc. But it's a cool little feature to have when you're trying to debug something and trying to work out why the thing's high when it should be low, for example. And then down here, we've got a very simple loop. We turn the LED off for high. We wait 1,000 milliseconds, and then we turn the LED low, which makes it turn on, and then we sleep for another 1,000 milliseconds, and then we just while loop round. So this code will never exit. You'll also see some of the examples do thread sleep infinite, I think. Gets the same kind of effect. Okay, so let's see if this deploys then. Hopefully it will. Deploy. Oh, that doesn't look good. No, it is actually deploying still. I think I've installed some kind of like code cop type validator. So I'm getting a lot more warnings and errors than I used to. Ah, there we go. So it's deployed. So we see here, we can see here we've got the internal versions of those bits of software on the device, and here's where we would see the error messages about the mismatch if we had a mismatch, and then we can see further down it's successfully deployed the software. I'm going to put the camera on because you'll see it's not blinking. And this is quite often the case. You need to restart the device to get it to rerun the code. So simplest way of doing that is to unplug it and plug it back in again. Hopefully we should see blinking light. Now this is the other thing I like about microcontrollers. From boot to that first flash was, I don't know, half a second. I don't know if you've got fast PC, but mine doesn't boot up in half a second. And I'd be lucky to unlock it in half a second. So it's one of the cool things about microcontrollers that even though they're not very high specs, they can do things a lot faster than you might be used to on a PC. Okay, right. Demo 1 done then. Back to the slides for a second. So yeah, so the nanoF tool puts the software on, puts the libraries on, and I think it's actually used by the tools in the background to put the code onto your device as well. I think what's happening in that output window is it's actually running that nanoF tool with a binary image that is developed from the platform. Got a question?
Is it running on your PC?
No.
Or it's actually running on the device? And there's a library that's kind of syncing it up so that, because you said you could breakpoint. So there's some debug tool that it also installs, is that when it does that deployment? Some little debug gizmo that allows you to breakpoint and...
Yeah, that's kind of halfway house between the two. So you can like in any dotNet app, you can run a kind of release version and not debug. And in fact, that's what's happening here. This isn't running the debug version,
right?
Because the debug's not running.
It's just power.
Yeah.
It's now just taking power. So if you ran that,
so when it's running
without a laptop, it would still flash.
Yeah, and I could just plug it into a power socket and it would still do its thing.
Yeah.
You obviously can't do that with the debugger, but potentially you could see the serial output. You don't necessarily have to have a laptop or a Windows device to be able to get access to that debug information. I would recommend it's probably a bit easier. On the topic of things that are easier, I'm using Visual Studio. There's a plugin also for Visual Studio Code. It mostly works. I found it to be a little bit temperamental and just a little bit more finicky getting stuff to run. So I would say if you're a kind of hobbyist, then that's fine. Spend the extra 20 minutes getting that first deploy working. But But if you obviously were doing it for a professional thing, then I would recommend using the Visual Studio plugin, which is a lot easier to use. Okay, so done the blink. Next up. Okay, so the serial peripheral interface is a common industry standard for microcontrollers talking to other devices. And the ESP32 has got 4 buses, but it uses 2 of them, so you can't get to them because it needs them for the Wi-Fi. But then it can host multiple devices on each bus. So it gets a bit confusing sometimes of what's running what, but it then gets more confusing because you can remap the pins. So old school microcontroller, pin 1 was always TX or ground or whatever, and it can never be moved. Whereas on these more modern microcontrollers, and it's not just the ESP, it's all the STMs and Raspberry Pi ones as well, they can move stuff around. So if you get your board layout wrong, you can swap pins over. If you get transmit and receive the wrong way around, for example, you can swap them around. It depends on the device, how much you can do that with. Some things have got only certain pins will do certain features. More modern chips, pretty much, it's open field. All pins can do pretty much anything. I think there's obviously power and ground, and then all the other pins can be reconfigured to be whatever you want. So they can be talking to the memory, they could be talking to the screen or the touch screen in this case, or on this device also can talk to the SD card bar. Serial peripheral interface. Now, we've got 4 pins that make up that interface. We've got a clock pin, we've got data from the microcontroller to the device, and we've got data from the device back to the microcontroller. And then we've got the last pin, which is a chip select pin. So as I mentioned, you can put multiple devices on the same bus, and it's that last pin that does the kind of clever switching between the different devices. So you enable one device, talk to it for a bit, turn it off, enable the next device, talk to it a bit, turn it off, and they can all be wired on the same data and clock pins, with each one would have its own separate chip select pin. So, yeah, let's have a look at some more code. Yeah, screen test that'll do. So here we can see some of these pins getting defined as constants. So chip select is 15. I'll have some other pins probably a little bit further down. What did I do with them? Here we go. So pin 13 in this case is the master out serial in, which is also known as I've forgotten the modern terminology. They got rid of master slave and they've replaced it with controller and peripheral. Yeah, so that would be controller out, peripheral in, and then clock's just clock, and then the bottom one would be controller in, peripheral out. So basically your TX and RX in other words. So this remapping of pins is specific to the ESP library. So other devices have got different ways of doing that same kind of thing. So we map our pins, we set up our configuration for the SPI. Not particularly happy with the way they've done this library because they've kind of merged 2 things together. They've got the SPI configuration, but they've also got things like reset and backlight, which are very specifically about the display. So we configure the display config. This SPI configuration is actually display configuration, and it has the backlight in there as well. So basically, different types of displays work in different ways, but these particular ones have got a big flat LED behind them that basically shines through. That's how you see all the colours. Oops. Okay. So next up, we've got a graphic driver getting defined. I love this method name here. Graphic driver with default manufacturing settings. Goes on. What's the rest of it? Oh, settings. There we go. So they obviously named it as they saw it. And this here is the library for that particular device. So each kind of screen has got its own configuration. Part of that configuration might be the orientation. Other bits will be down here like width and height. But internally there'll be other kind of differences around them that you have to deal with. And one of them is the order of colours. So you're probably used to RGB, red, green, blue. But for some reason, a lot of devices decided to change that around. So this particular device is blue, green, red. So you'll see in the code examples that I've got lots of kind of remapping of the three colours to make them work properly. Otherwise, your green things come out. Oh, green things would be fine. Your red things come out blue, and your blue things come out red. Now, the other problem with the display is there's lots of lovely libraries that the nanoFramework people have created for doing display stuff, but a lot of them basically take a bitmap from the screen and buffer it on the device, and then you make modifications to it, and then you send the changes across, which is fine if you've got enough memory for, I think, what is it, 320 by 240 times 3 colours times, I think it's 6 pixels colour depth, or 6 bits colour depth. Basically, if you've got enough memory, you can do that. But this device hasn't got any spare external memory that you can do that with. So a lot of the core libraries I couldn't do anything with. So you'll see a lot of the devices will mention serial RAM that you can add into these boards, and strangely enough, the serial RAM also uses SPI to communicate. Okay, so let's have a look at the code. So we've picked our graphics driver, we've picked our screen configuration, we initialize the screen, we turn the backlight on the same way we did with the LED, just turn a pin and then we write high to it in this case, the opposite of the LEDs, nice and standard, thank you very much. And then I call a function to blank the screen out, and we can have a look at that in a second, and then I call another function to display text. I think I mentioned to some of the people while we were eating pizza, one of the problems with these devices is the resources that you're kind of used to having on a computer just aren't there on a microcontroller unless you intentionally put them on. And text is one of those things. It doesn't have the concept of fonts built in. So you have to put your fonts on. And of course that takes up space. So you need to think about what font you've got, how big it is. And again, things like scaling of fonts, that is also not built in. So if you want to have multiple font sizes, you may need to put the same text on multiple times. And we can do that with a tool. Where is that hiding? Do I have to load it? There we go. So there we got a resource there. So I've got Century Gothic bold 36. So the 36 is font size, bold is bold. And you'll see it's a tiny font type. and it's a bunch of bytes basically. So tiny font is a standard that people have put together that is being used across lots of different microcontrollers, similar to the sort of TrueType or whatever, but it's a bitmap font basically. So to get each of the letters on the screen, you have to have a bitmap of that particular font. There's lots of nice tools you can use for creating these tiny fonts, and you can say, well, actually, I'm only interested in uppercase letters, so you can just put on the uppercase letters. Or if you're only interested in numbers, you could literally just put on 0 to 9, and you could convert that in onto the screen. Okay. So let's dig into each of those functions in turn. So we'll start with display text. It's kind of easy. So we ask the resource manager to get the font, and we tell it which font we want. We then pick a color, and which we have to swap the red and the blue around to get dark blue. And then display control is one of the built-in tools, and we just write and we tell it some text, and then we give it a position with a little function that just centers it up. So just sort of takes the length and then divides it by 2 and offsets it. And then I just write my 5 lines of text using that display control. And that all works quite nicely. However, to draw graphics, as I said, I couldn't use the main library because I didn't have enough space, but I can take the data in the ROM and write it onto the screen directly, cutting out the RAM in the middle. And I do that with a very small buffer and literally iterate across the width of the image, the height of the image, and then write out each of the individual pixels one at a time. It's a little bit tedious, but I wrapped it in a function, so it's kind of done. And then for blanking the screen, I just do the same thing, but with a fixed color. So you give it a screen color, converts the tops of red and the blue around again, and then it just writes that out. I can't remember if yeah, so this one writes it out in little blocks of 10, just to speed up that process slightly. Right, let's deploy that one then. Oh yeah, so you'll note on the solution now, I've got the graphics library as part of my solution as a separate DLL, to use a better name. The reason for that was, as I said, different displays got different features. For some reason, when they wired this particular one up, they swapped the X and the Y over. So all my text was coming out backwards. So I had to go into the library and find the initialization string, which you can get off the datasheet for the display, and just swap a couple of lines of code around to make the X and the Y go in the right place. I will, at some point, try and push the changes upstream into the solution. You'll see in a minute when I talk about the touchscreen why that might not happen very quickly. Okay, so if we deploy that, should build it. And there we go, and it's deploying blocks of bytes. So yeah, as far as I'm aware, this is the nanoF tool running. Successful. Just going to swap the screen over. Might get a bit of a reflection on that because okay, so boots up. There we go. So hopefully you saw that kind of wiping effect across. That was the blocks of 10 getting drawn across. So we'd added memory buffer, that would have been faster, but something to kind of bear in mind, which is you kind of started to hit the limitations of the device performance for writing to the screen. Okay. So there's the fun of SPI and displays. So when it comes to the touchscreen display, this is also an SPI device. Unfortunately, there wasn't a library for this one. So I had to get the data sheets and I had to understand how the device worked. And then I gave up and found somebody that had written it in C and translated it back from C into C#. To do roughly the same thing, and then had to do a bunch of optimizations around the way SPI works differently on dotNet framework than it does in the world of Arduino and C, etc. So what I mean by that basically is when you, I mentioned we've got those various different pins, and we've got chip select, 2 data pins and a clock pin. So on the world of nanoFramework, when you ask it to write to the display, it will enable it, send a bunch of data, and then disable it. So the problem with the library that I ported was it was getting things in chunks. So what I had to do was basically to overlap all the commands. I don't know if it, yeah, kind of, this is what this sequence here is trying to explain. So basically what you do is you ask for the X coordinate and then you ask for the Y coordinate, but while it's asking for the Y coordinate, it's reading the X coordinate. And then you ask for the Z coordinate, which is the kind of pressure that you're touching. And while it's doing that, it's getting the Y. So it's all kind of overlapped and offset. So you'll see here we send some data out and then we start getting the data back in afterwards. And yeah, what was happening was this chip select line here was turning off after the first 8 bits, and hence it never got any results back because it resets it when it turns it off, basically. Yeah, so there's lots of fun with the data sheets. I use the debugger quite aggressively on that one. And also, yeah, kind of, it's obvious if you work with integers and floats a lot, but my world, I'm dealing with money all the time, so I'm always using decimals. And I've forgotten about that. So when I take my integer numbers and I divide them to sort of scale the screen, so the touch pad is 1,000 across, but the screen's only 300 across. So I scale everything by a factor of 3. And of course, you get all the rounding problems of doing that with integers. So I kind of tweaked the maths a little bit to solve those kind of problems. But yeah, it's kind of understanding that kind of limitation. Oh, yeah, the other thing about maths, and I've mentioned this a few times already, you kind of assume the functions are built in like absolute and math.absolute, but it isn't. You have to include that as a separate library if you actually want to use that kind of thing. So I ended up writing, I just wrote a 2-line bit of code to do absolute. Interrupts. So on a day-to-day on your laptop or PC, interrupts are happening all the time, but you don't really get to see them or play with them. So basically all the different bits of hardware are constantly going, oi, computer, I've got some data for you. Oi, here's a bit of data. And they all kind of coordinate between themselves by a series of interrupt handlers built into the operating system. We don't have those in the nanoFramework, so we've got to write our own interrupt code. But thankfully, it's not particularly difficult. So let's move to the next solution. Touchscreen, there we go. Yeah, one thing I hate about doing these kind of presentations is when I go back, I'm going to have to reset all my settings because these fonts are about 12 times bigger than I usually have. Okay, so touchscreen, very similarly, has a bunch of stuff similar to the graphics one. So we do the setting up the pins for the display, we set the display, we set the driver, we initialize the driver. we turn on the backlight, we blank the screen, and then we set up some more pins. So say we've got 2 buses. So we set up our, oh, can't see it's off the side. Oh. There's it gone, there we go. We set up our second SPI bus, which is, according to the data sheet, technically the 4th SPI bus. And this is one thing you'll see a lot in microcontrollers, which is the names the software gives to things are not necessarily the same as the physical pins on the device. So even to the point of, I can't remember the earlier code, it's IO18, I think, for the red pin. That's not necessarily pin 18, there will be a remapping of that. So it's one thing to be kind of aware of, is pins are never where you think they are. But the ESP32 is fine, we just configure them. So we configure the second bus for the touch screen. And then we've got a slightly different setup. This one doesn't have any display specific stuff against it. This one's bus number 2. And then we create an SPI device with the configuration. And then we go away and use that for doing different bits and pieces. Yeah, let's just talk about that for a second. So I mentioned that the touchscreen driver didn't exist. So I started writing the driver, and then I told the nanoFramework people, hey, I've got this driver, do you want to accept it? And they went, oh, sure, just go through our quality control process and we'll let it in. So I was like, oh, they're going to want unit tests and stuff. It's like, nope. They want all the functions labeled, and all of the comments have to have a full stop on the end of them. And you have to have 2 spaces after a function name or 1 space after something else. So basically, it took me 3 months of little tweaks here and there, because they're part-time, I'm part-time on this. It's not my job to do these kind of things. But eventually we did get it through. So although I do have the code installed locally, you can download it as a NuGet now and use this device. Nice and easy using the examples. Yeah, so using statements, iDisposables, for those that are familiar with them. The idea is that this is a resource that you need to deallocate when you've finished with it. So we create a controller, we create our touch screen, that's this XP2046. We've got a new pin, and this pin is a little bit different. So it's not an output pin this time, it's an input pin, and it's an input with a pull-up, which basically means if you don't connect anything to it, it'll be high. If you connect high to it, it'll still be high, and if you connect low to it, it'll be low. So when you're doing inputs, you have to know the kind of characteristics of the thing you're connecting to, and whether it's going to properly pull things to ground or whether it's not. So in this case, they told me how it worked. I read that big long data sheet. So I set that up as a pull-up. I said they love their names. And then we register a callback for pin value change event. Kind of does what it says in the tin. So that's going to create a function pointer basically. So when the input on that pin changes, it calls a bit of code. Now, I had a bit of chat with them at this point, because in the microcontroller world, when you're dealing with interrupts, the code in the interrupt handler needs to be as small as possible. Because while it's in that interrupt, it can't be doing anything else. And they said, it doesn't matter, in the nanoFramework, we've got all that covered for you. You can write as much code as you want. So I ignored them and wrote as little code as possible. So in my callback function, which is down here somewhere. There we go. Basically, I've got a variable gets updated. And again, something that you have to be aware of in the microcontroller world, you basically have to tell the compiler that this function is going to get called somehow, because the compilers don't understand it, and you have to set this as a special volatile type of data. Don't need to do that in nanoFramework, it sorts it all out for you. So this is just a normal Boolean variable, which I set to true. And then in my main loop, basically I say, well, in fact, if it's touched, then I'll go off and get the data. So it gets the point, and if the point's less than the value, what do we do? Hey, so I remember now. Sometimes the sensors gets completely confused and gives you a negative value, which is obviously not on the screen. So just a little bit of error handling to deal with that. And in fact, you'll get negative values if there's no touches as well, just the way the touch sensor works. So this first block here is basically to deal with no touch. And then here we've got touching, where X is less than 50 and Y is less than 50, and it displays text blue. And why don't we just run it onto the device and we'll see what that's doing. Oops. Deploy. Yep, so that'll be bigger than the other ones because it's got both graphics and thing. And again, it didn't reset itself, which I wasn't expecting it to. So let's start it up. You can't see what I can see, so let's have a look at the camera. So I've got 4 coloured squares: a red square, blue square, green square, and far corner is yellow. Normally use this with a stylus, but you can use your finger. So if I press blue, it goes blue. If I press red, it goes red, green, and then oops, yellow in that corner. So basically, simple graphic routine to do these buttons. Imagine if you then sort of take this to the next level, you can have buttons for like interactive menus or picking your radio station, etc. And the reason I mentioned radio stations is because that's one of the things I want to do next, which is an audio output on there. I haven't done it. There's an SD card, haven't touched that. Wi-Fi does look to be pretty straightforward actually. Other people have used Wi-Fi quite a lot. But again, coming back to the point of things you know just are there already on the computer, are not there on nanoFramework. So you actually have to tell it every time you start the device up to connect to the Wi-Fi, because otherwise it would just not think of doing that. And yeah, I want to do some more graphics. And a new one in just this week, I discovered another board of a very similar price bracket, but it has e-ink on it. Now the clever thing about e-ink is that you write messages to it and then you can take the power away and the message stays on the device. So I don't know, are there any Waitrose shoppers here? Nobody wants to admit to that. I was in Waitrose at Peterborough at lunchtime, trying to find a cable, which they don't sell, by the way. What I did spot was by the batteries and by all the other displays, they had these little e-ink tabs on them. So they look a bit thicker than a regular price tag, and somebody can go around and they can update them during the day or whatever. And my company is hoping to do something similar in this year's hackathon, which just brings us right back to where we started. So that's me. Here's some of my other crazy projects. And if you want to know anything more about them, you'll have to wait till after Andrew's talk. Are there any questions? Any quick questions?
So how much is the device that you've got there?
So this one came from AliExpress and cost me about, I think I bought 4 of them because I was buying them for prizes. So it was about £10 each.
Including the screen?
Yeah.
Well, that's pretty good.
Yeah, so you get a box, you get a cable, you get a little add-on that allows you to sort of wire external devices to it.
Right, and it's just an anonymous prototyping board, but it's ESP32 chip.
Yeah, so they're known as the cheap yellow displays. There was a guy called Brian Locke came up with the idea of naming them that after he did a lot of work with them. Because they're yellow and they're cheap and, and they're a display.
Yeah.
But yeah, there's other boards in other shapes and form factors, and slightly different functions.
Right, and there are other architectures of microcontrollers that you supported, but is Raspberry Pi Pico included in that? Do you know? 'Cause it's the only microcontroller I know about.
I'd have to look it up, to be honest. I know the STM32s are, which is another big. That's used in some of the
like
more high-spec
2040 or
Arduinos.
something.
But I don't know about the RP.
2040. I think it's their own controllers.
I wouldn't be surprised, but I've not dug into it just yet.
Okay. Right. Okay. Thanks.